Welcome back. This is CET 4333, Computer Organization. I want to continue our discussions from where I left in last lecture. We are looking at RTN description of the branch instructions. Branch instructions are such as go-to statements, or when you want to basically interrupt the flow of the execution of the one instruction after another instructions. Then, for example, you call another function and then you execute that function, then you come back and start. So those conditions, how we are explaining those conditions in RTN. In RTN, we said we define a variable as cont. The cont, we rename the cont as 3 least significant bits of C3 field in the instructions. This tells me that the branch instructions are type 3 instructions, meaning they have an opcode, or A field, or B field, or C field, and C3 field. So then in C3 field, we look at the least significant 3 bits, and we say if it is equal to 0, never jump, or never branch. If it is equal to 1, we say always jump. This one is equivalent to go-to statements in the C language. If it is equal to decimal 2, that means that branch if content of R of RC is equal to 0. In RC field, it's a 5 bits, 0 to 4, and could have a value between 0 and 31. It's 5 bits, right? 2 to the power of 5, 32. So it could have a value between 0 and 31. So you go to that number, that register number, and take the content of that register number. If that is equal to 0, then you branch. If it is that C3 field, if it is equal to 3, only the 3 bits, the least significant 3 bits. If it is equal to decimal 3, then if the content of our RC is a non-zero value, then you jump. And that means if positive or 0, right? And if that's equal to 5, then you look at the content of the R of RC, bit 31. Only the bit 31 of R of RC. If it is 1, that means if it is negative, jump. You remember the most significant bits, if it is 0, it is positive. If it is 1, it's negative, right? And that's what it is here. And if it is 4 and 5, then we look at the most significant bit of R of RC. If it is 0, you branch. And if it is equal to 1, which means if it is negative, you branch. How the instructions work? Conditional branch, or this way you say branch if the opcode, the value of opcode in that 5 bits, most significant 5 bits, if it is equal to decimal 8, then if condition is true, meaning one of these things, condition is true, then R of RB is stored in PC. Meaning then we jump to that point because you put the new address in PC, so we fetch that instructions from PC, from the memory. Branch and link, this means that whenever we say branch and link, it means that we store the current value of the PC in a register, and then we branch to another location in memory. And the reason is, so when we finish that part, then we can come back and start exactly where we left our coding. It's like a function call, then once you return, you start from the next instructions. So first, if the opcode is 9, then first we load the content of PC to R of RA, and then if the condition is true, because we want to jump, right? If the condition is true, then we load the R of RB into PC, and that's the new address of that we want to jump. Here are some arithmetic instructions. If you remember, we said in arithmetic instructions in this SRC computer, it requires to have 3 registers available. It's a 3 register operations. That means that we bring the operands from memory and load them to these 2 of the registers, and then we perform the operation and we store the results in ROR-A. All right? And then if we want to save them back to the memory, we take the content of ROR-A and take them back to memory and store them right there. So if the opcode is 12, then ROR-C is added to ROR-B, meaning the content of RC, register RC, and content of the register RB added and loaded to ROR-A. Add I means one of the operands is immediate operands. One of the operands, it comes with the instruction. It is on the instructions. So that means you go to, or you take the content of RB, you add to the C2. When you see C2, that means this instruction is type 2 instructions. That means it identifies RA field, RBB field, and C2, and has an opcode, of course. So you add the content of the ROR-B and you add it to C2, which is one of your operands. So this one it comes with the instructions, but this one you have to go to memory and get them and bring them and load them to ROR-B, and then add these 2 together and then load them to ROR-A. Okay, and the same description goes for subtractions, negations. Negation is you take the ROR-C, you negate ROR-C, and you load into ROR-A. Always in arithmetic operations and logic operations, the destination is ROR-A. And the other operands come from ROR-B, ROR-C, or the constant field. For example, AND operation, you AND content of ROR-B to content of ROR-C, and you load them to ROR-A. Now, and I means one of the operands is in the constant field. So you take the constant field and content of constant, that's 17 bits, and you AND them with the content of ROR-B, and you load the results in ROR-A. Always, this is one of the principles of the programming, that we want to make sure that none of the operands change its value. If you notice that, if I want to negate or complement content of a register, for example here, I negate them and then store the results in ROR-A. So ROR-C doesn't change, right? And if you notice here, this means and, this sign like a V means or, and this sign means not or complement. Here is the shift instructions. Shift instructions, first we want to know the number of bits we want to shift, whether right or left. Okay? The shift instruction, that number comes from the most significant 5 bits of, depending on the value of the most significant 5 bits of the C3 field. If that most significant 5 bits is equal to 0, then the least significant 5 bits of ROR-C will give me the value of n, the number of bits we want to shift right or left. If the content of that C3 field, the least significant 5 bits of C3 field, is a non-zero value, that number is the value of n, meaning the number of bits we want to shift. Now, shift right is, it says, you take ROR-B, you want to shift them to the right. If it is 2 bits, you load bit 31 to bit number 2 and transfer them to bit 31 and 0. Now, first you put, if n is 2, you put 2 zeros, and then you do this operation. Let me see if I can show you on a piece of paper. Let me turn on the document camera so we make this one clear. I did record this section, but the server lost them. That's why you see this one is already written. This is my second time recording this lecture. All right, shift right, if opcode is 26, that means out of our A, 32 bits out of our A gets whatever the value of n is, 2 zeros, concatenated bit out of our B, 31 to n. What is that telling me? If n is 2, if n is, let's say, if n is 1, then I put a 0 here, right? And then I move all these bits to here. So this one moves out, right? The movements is in this way. You shift everything one bit to the right, and once you replaced the empty spot here, because if you shift everything over there, this one is going to shift here. As you see, that 1 came to here. So what's going to be in this one? We're going to put a 0. So if n is 2, I'm going to have 2 zeros and then shift this one here. So then it's going to be, and out of RB 31 to bit 2. From here to here, from here to here. So because 2 bits goes out, right? 31 to this one. Right? So you put 2 zeros, and then from here to 2 bits, move them here, and then you take this one and load them to RORA. It is very kind of straightforward. And shift right arithmetic means shift right arithmetic means exactly the same thing, except here instead of putting a 0, you put the most significant bit or the signed bit of RB register. If it is 0, you put a 0. If it is a 1, you put a 1, and the rest is very much same thing as here. And the shift left is exactly the same as shift right, except you're moving to the left. So you're shifting to the left, and so you put the how many zeros you're going to put. It is on the right hand side, right? Because then that what it means. What it means that if this shift left, it means you moved on this side. So you put the sign bit of this one here. It is 1, 1. And then from this bit, you put everything. Starting from this bit, you put everything here. So 1 comes to here. This comes there. All the way. And if it is 2 bits, then these 2 bits move up because this 0 comes here, 1 comes here, and it's just shift left. And then shift constant. How many bits to shift constant? And it's exactly the same thing. And how many bits you want to shift, you just shift them in the same fashion. This is exactly the same codation. Now, here's the shift right arithmetic. An example. R2 register is this. All right. It says arithmetic shift right by 13. By 13. Shift right arithmetic R1, R2, 13. That means shift R2 register by 13 bit to the right, right? And then store the results into R1. If I shift 13 bits to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this goes out, all the way shift out. From this 1, 1, 1, it starts coming in. All right? And this, you see that 1, 0, 0. This is exactly the same as here. What do we put here? We put exactly what is the most significant bit of the R2 register, which was 1. So we put all 1. That's the arithmetic. If A wasn't there, I would have put what? All 0. And here are some examples formal assembly language instruction. Shift right RA, RB, RC. And this means shift RB right into RA by 5 least significant bits of RC, whatever is in RC field, meaning in the RC field, right? And same thing, whatever it is in the, when it says count, that's in the 5 less significant bits of instruction that comes in. Shift right arithmetic, a shift to right into RA by 5 least significant bits of RC. By shift right is a shift RB right into RA by 5 least significant bits of instruction, because it says count. Here is RC, this is by the instructions, RC by instruction. Exactly the same thing. Shift RB, this was a shift RB circle into RA by 5 least significant RC. What is this telling you is, let me go back here. Sometimes, let's do it in 8 bits, so I can. All right. If I'm going to do shift right circle, what's going to happen? I am. Let me get these here. Then you can see. If I'm going to shift 2 bits, that means these 2 bits are going to go out, but are going to come back and get to here. So that would be 1, 1. And then the rest are from here. So that would be 1, 0, 1, 1, 1, 0, 1, 1, another 1, and a 0. So 1, 0, 1, 1, 1, 0. All right? In a circle pattern. It's like a rotate. All right? That's what it means. Here's the NOP operation and stop operation. NOP operation means if the opcode field is 0, then do nothing. No operations. The reason we do that, to buy time. And you will see it is very useful, for example, if you're doing pipelining. Pipelining meaning we don't fetch one instruction at a time. We fetch, if I fetch one instruction, then I'm busy with doing an arithmetic operation, whatever operation in the CPU, then I have opportunity, the bus is free to fetch more instructions. Right? Have them ready, buffer them in some place in memory, in CPU. So we have, so save time in fetching the instructions. So what happens if one of the instruction is jump, then I have to trash all the instructions after that one and jump to the instructions that it's in memory and go get that one. So in those kind of operations, which is the topic of chapter 5, I will explain that after chapter 4, we use the NOP operation, comes very handy. Stop operation, if opcode is 31, that means we want to stop the execution and go to fetching the next instructions. You load the 0 to run. As soon as run becomes 0, then you are done with that. And also, we have to understand the SRC, Simple Risk Computer, also it's a machine language, right? Because every CPU has its own language, so this is also its language. However, RTN is a specification language, meaning specification languages are languages that are used to specify other languages or systems. And there are many examples for those, like VHDL, Verilog, YACC, LEXs. So if we write in RTN, if we want to design a computer using the RTN, then we run whatever we write with the compiler that generates SRC instructions, like an assembly. And then that one gets to be executed or simulated, and then we know if our design works actually. Then we take him to the manufacturer to get them implemented on a chip. These are some explanation about the RTN. They allow the description of what without having to specify how. They allow precise and unambiguous specifications like natural languages. The main thing is when we explain the operation of a computer or the design using the natural languages such as English, there might be some misinterpretation or misunderstanding. However, if we use the RTN, everything is clear, because as you will see once we get to chapter 4, how I'm going to use this RTN to describe the operation or the design of a processor, then you will see it is unambiguous, it is clear, and everybody understands exactly at what is going to happen at what clock tick. So that's why it's called an RTN, a specification language. It's clear, it's easier to understand. Here are some addressing modes described in RTN. For example, if the address comes in a RTN format, in a register, we call them a register. Register indirect means if R of RA, for example, R of A, if it holds my operand, then that's loaded to R of T. That means the register has the operand. If the register has the address of my operand, that's called register indirect. If a value is in my constant field as an X, that's immediate addressing. Direct, an absolute address means a memory location is given to you, the address of operand given to you. That's a direct absolute. If address of memory location is given to you, meaning an address given to you that you go to that location in memory, then content of that memory location is the address of your operand. That's the M of X. That's indirect. That's like a pointer in C language. And then we have indexed and relative. The indexed or displacement means one of the registers, content of one of the registers added to a constant, and that gives me the address, memory address of the operand. Relative means the content of program counter register or PC added to a constant value gives me the memory address of my operand. And increment, auto increment, means RA gets R of RA plus 1, and auto decrement means R of RA gets R of RA minus 1. So first you load the memory location and then you increment them or decrement them and bring them back, and you have the right address. Now here are some register transfers that can be mapped to digital logic. How do we do if RTN statement says B to A? What does that mean? It means if B is a 1-bit, A is a 1-bit, all right? B is here, this is a D flip-flop, rising edge clocking system here, and I'll explain to you here what it means. It means if I stroke, what happens? The output of the B gets into the A. Isn't that's exactly what you want to transfer B to A. So if B is 1, you see here's the 0, B is 1, clock ticks at this point, then A is 0, right as soon as the clock ticks, at the rising edge, the value of A becomes exactly the same as value of B, because B gets loaded to A. It is 1, becomes 1. Now if I put a little bubble here, that's the trailing edge system. That means when the clock comes down, then this guy receives the output of B register. That means A follows B at this point. It comes straight here, it goes up, and that would be the trailing edge D flip-flop. Now if you have more than 1 bits, you put them in sequence, 1, 2, 3, and you connect all of them to the same strobe. With one strobe, everybody receives the value of those. And we can also show it this way, abbreviated notation, that you say B M to 1, how many bits they are, and we started with 1, 2, 3, so we say M to 1, or if there are 32 bits, you say 31 to 0, and then you put a line, then you say here 32, and with one stroke, which is exactly the same as this one. Now, how do we gate the data? We always connect them to an AND gate, and we know anything ended with 1, that anything goes up. Anything ended with 0, that anything goes up. So basically, whenever I have 1, whatever the value of this guy is, if this is 1, 1 is going to go up. If this is 0, 0 is going to go up. If this is 0, I don't have anything going up, right? Because it's always 0. That means it's not the correct data. And we use these gates for that fashion. If I want to, this is OR gates, that means you get both of them out. And this is exclusive OR gates. Exclusive OR gates, then you get also one at a time. And the same way here. For example, if I have a control input and the data here with the exclusive OR, if control data is 0, then the data is out. Because anything AND ORed with 0, that anything goes out. And if the control is 1, then complement of data goes out. And the same concept here, 2 AND gates, and then you connect them to 1. This means the data from multiple sources can be selected for transmission. If there are 10 AND gates here, then I can turn one of these gates, gate X, gate Y, gate Z, whichever I turn them on, set them to 1, that data is going to be routed out. And this is exactly the same concept it is used for multiplexer. If I want to get this guy out, I turn this one on and keep these other gatekeepers 0, then this data M will go out. And the same concept again here. As you notice, the separating merge data, it's very easy. If the X and Y coming in, I keep him 1 during the X, I keep him 0 during the Y. When the X comes in, since this one is on, what happens? X goes out. You see M, it's X. What happened to the Y? It went only 0, because anything ended with a 0 is going to go out as a 0. Anything ended with 1 will go out exactly whatever it is. If it is 0, it will be 0. If it is 1, it will be 1. So it will be X. Clock is on during the X. And this is again the same concept with selected gate and strobe determine which RT is going to take place. For example, C to A and C to B can occur together, but not C to A and D to B. D to B. So what's that mean? C, if I keep this one at 0, turn this one on, this comes out and goes in, and then if I turn this one on, this will go on exactly right here. So C can go to A, C can go to B. And but C can, as you see that C is going to A and D is going to whatever, wherever we want to send it, occur together. So it is very kind of straightforward, and because the gates, however we turn the gates on, these are the gates, however we turn this one on, we can have them in the same order coming through the OR gates, and then whichever of these gates is on, and that one will receive these informations. And here is the open collector NAND gates output, explaining how the NAND gates work, and so on. I'm going to stop here. There are a few more slides that I have to put in my next lecture, which will be today, because I'm closing to the 30 minutes. That's how I lost the, once the file gets close to 2 gigabytes, the server is dropping it. So I'm going to stop here, and I will post another lecture for the rest of these notes.